So what's up guys, this is me again, your resident chemistry tutor Mark, and welcome to the part 3 of our 3-part mini video series for chemical kinetics. Now, if you notice, and if you're watching closely in our in the first 2 videos for this mini series, you have noticed that I have changed the collision theory of chemical reactions into theory of chemical kinetics, because I will be including another theory for chemical kinetics in this discussion. So for this video, I will be talking about, as I've said earlier, the theories of chemical kinetics, and also I will discuss at least briefly about reaction mechanisms, which will include also catalysis. Now there are two theories on how reactions proceed. So one theory, the one that will be thoroughly discussed in this video, will be the collision model. So by its name goes, collision models. The collision model states that reactants form products when they collide together. Now, in order, what do you call this? Now, the greater the possibility that they will collide together, the faster the reaction will proceed. Now, if you look at this, wait lang. If you look at this video here, if you look at the illustration here, this shows that you can explain using collision theory or the collision model why an increase in the reactants will also lead to an increase in products. Now, when you increase the reactant concentration in the solution, since the space, or rather the volume that they move, will also be the same, will remain constant, or will still be the same, there will be more chances for them to come in contact together to form products. So that is what they call this, a more general view. Now, in the collision model, this is an application of your kinetic molecular theory, wherein, or an application, or rather, pwede man nga derive siya from kinetic molecular theory, wherein the reactants move in the solution. The reactants move like particles in the solution. They move in the translational motion. So in the collision model, you only assume the translational motion of the molecules here. Now, siyempre, during their motion, there will at some point that they will collide with each other, and once they collide, they will form products. Now, the collision is not just simple collision, but rather effective collision. Consider the reaction here, illustrated here, the decomposition of nitrosyl bromide to form your nitric oxide, or your NO, and your bromine molecule. Now, in order for that to occur, if you see in this video, the bromine molecules should collide. The bromine parts of the nitrosyl bromide molecule should come in contact together, or should collide, so that this one here, when they collide, they will stick together, and this part will detach to form products. Now, it is also possible na amoy siya ng orientation as long as it is the bromine molecules, it's two bromine parts of the nitrosyl bromide molecules that will come in contact with each other, para they will form bonds here, and these two will detach from the parent molecule. Now, if you look at part C here, when diri naman niya, the nitrosyl part is the one that collided with each other. So when they collided, since the product is nitric oxide, you just need for this one to detach, and collision does not enable it for them to detach away from the molecule, because at the same time, when at the same instance, when there is collision of the molecules, dapat they should attach with each other here, since this one will detach away from the molecule. they should also attach with each other here. So if these parts will collide, they will not, the bromine moieties will not touch with each other. Thus, they will not form bonds. They will not form bonds, and no reaction, no product formation will occur. Thus, no reaction. Now, as I've said earlier, collision model is derived or an application of the kinetic molecular theory, but and since we involve collisions here and translational motion of molecules, that means those translational motion, they have kinetic energy, and when they collide, their kinetic energy should be sufficient that upon they collide, they will overcome this energy, an energy barrier here for them to form products. And in this energy diagram here, this is the energy barrier that they will have to overcome, and that energy barrier is what we call the activation energy. Now, if you remember your kinetic molecular theory, guys, that an increase in the temperature will also increase the kinetic energy and in turn the velocity of your gas molecules. Now, the same way is applicable here. Since an increase in temperature, the velocity of the molecules will the reactant molecules or particles will increase. The chances that they will collide with each other will also increase. Thus, the faster the reaction will proceed. Now, that is on a molecular view. Now, if we look at on a macro scale, if we look at an actual data, the temperature affects the rate of the reaction by affecting the rate constant in the rate law of that reaction. So, if you see in the graph here, an increase in temperature in Kelvin will also result to an exponential increase in the rate constant of the reaction, and that relation is shown by the Arrhenius equation, which is shown here, wherein EA is our activation energy, the temperature T is our temperature, and R is the same as ideal gas equation, which is our gas constant. However, the value and the unit will now be different. In the ideal gas equation, the gas constant there is 0.0206. 0.0206, right? Liter atmosphere per mole Kelvin. Now, in the the value of the gas constant will be 8.314 joule per mole Kelvin, since we're now dealing with energies here. And your A will be the frequency constant, which is unique for every reaction, just like your activation energy. So let's dissect the frequency factor. Now, the frequency factor is actually a product of two other factors, the P and the Z. So what is this P and Z? Now, the Z is the collision frequency and P is the orientation factor. So what does this mean? So Z, by its name, collision frequency, it's how many times do these molecules collide per unit of time at a given amount of time. So that is what we call collision frequency. Now, if you can see it here, if you increase the collision frequency, this will also increase the frequency factor, or sometimes they call it Arrhenius constant. Now, in turn, if you increase the value of the frequency factor, this will also increase your rate constant, and at the same time, it will increase the rate of the reaction. Next is our orientation factor. So we have already discussed there that the collisions should not only be the reactants should not only simply collide with each other, but should collide effectively with each other with the proper orientation, and that is accounted by the orientation factor. So the orientation factor is the percentage of the effective collisions produced by the reaction out of the number of out of the total collisions that it makes at a certain amount of time. Now, for example, if the collision frequency is, now for example, if you have 10,000 collisions occurring per second, so the orientation factors show that from the 10,000 collisions there, how many of them will be effective, or rather that will lead to product formation. And this exponent here, this one here, is shows the fraction of reactant molecules wherein at a certain time its energy is greater than or equal to that the activation energy. Now, if the energy of the molecules, or the total energy of the reactant particles, will be this one, it will be greater than or equal to that of the activation energy. That's only the time when they can form products. So that means kung energy nila amune, when they collide with each other, when they effectively collide with each other, they will surely form products. Otherwise, even if the collision is not effective, but their energy is not greater than or equal to the activation energy, then no reaction or product formation will take place. Now, what do you call this? Now here, from the Arrhenius equation, we can also derive the line what do you call this? The slope-intercept form, or the linear form of the Arrhenius equation. So the final form will be this one here. So I'll show you first how it is derived. Wait. Oops. So, we have ano de, diba? So, wait. We have, let's start with our Arrhenius equation. K is equals to AE, which is, hindi siya kitaan. Oops, ara. Nice. Okay. Negative EA over RT. So that is our Arrhenius equation. Now, let's perform a natural logarithm to ln to both sides of the equation, because whatever you do on one side, you also do on the other side. Amo nang rules when we're doing equation manipulations, right? Now, in our logarithmic laws, now if we get the logarithm of a product, this is equals to the sum of the logarithm of each of the factors. So let's say if we have log xy, that is also equal to log of x plus log of y. Now, since the natural logarithm is a logarithmic function as well, so we apply that law. We can apply this property of logarithmic functions here. So we'll try it here. So ln k is equals to ln. Oops. Wait lang, guys. Ara. ln ln A plus ln E over EA RT. Okay. Next board. So we know that in the logarithmic functions, when you raise a logarithmic function to a when a number is raised to a logarithmic function whose base is equal to that number, for example, this one here, so a raised to the logarithm of x base a, oops, galag. Wait lang guys, I'll troubleshoot this, I'll be right back. Okay, let's see if this works perfectly. So again, for example, if a is raised to the logarithm of x base a, wherein the base of the logarithm is equal to the number of the base kung diin nga siya nag-exponent. So they will cancel out with each other, and what you're left will be the x. Okay, just wait for a while, guys. Medyo galag ang akong panan. So we shall see. Sorry. So going back to our equation here, if you can see, since ln is a natural logarithm base of the natural number e, that means this will cancel out. They will cancel each other out here. It's lagging naman.
5 minutes later.
Okay, my apologies for the technical difficulties. I don't know what happened. Maybe the internet broke. Our internet connection. What's that? Broke down or something. Anyway, going back, we have this logarithmic property here that the logarithm, when the logarithm of a certain value whose base is another value, let's say a here, is raised to the same value as is the exponent of the same value as that of the base, what happens there is the logarithm of base a cancels and the a here cancels out, which will leave you with the value of x. Now, since the natural logarithm function is also equal to the logarithm function, the logarithm of a value base to the natural number e, that means we can apply the same thing to here. So this will cancel out, and what will that leave you will be ln k is equals to ln a plus negative EA over RT, right? That will, rearranging the equation will give you ln k is equals to ln a, is equals to negative E sub A, or activation energy, over RT plus ln of A. Okay? Which ang ginpakita ko, which I have shown in my slide just now. There. Okay? Or rather, here. Wait. which is viewed here. If you can see it there. Amo na siya. Now, as I've said earlier, this is our line equation. Now, if you're familiar, I'll just write it down here. If you're familiar with the slope-intercept form, which is y is equals to mx plus b. Forgive my penmanship. I'm drawing this using just my mouse. So, now this one here will be your y. Wait lang guys, someone's calling me through the phone. I'll be right back. So, sorry guys, my mom just called. Sorry for the interruption. Anyway, so here, for our slope-intercept form, this one, the ln or the natural logarithm of the rate constant will be your y, and this is your slope, or your m. Sorry. It should be, this is m, and this one will be your x, and this one naman will be your b, or your y-intercept. Simple as that. Okay, I'll just wait. Okay, so from the equation, let's try applying it with our set of data. Now, here I got this set of data from TRA. Now, the decomposition of the ozone shown here is important, blah, 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 blah. Now, the reaction here is the decomposition of ozone to oxygen gas and to your oxygen radical, or your molecular, or your unstable oxygen species. So, now this, the reaction was monitored using the reaction was monitored at different temperatures, and from those exhaustive data collection, these sets of data were produced. And now, based on this set of data, we determine the activation energy and the frequency constant of the reaction. So in our Arrhenius equation, that will be our E sub A and our T. The T, rather, the A, or our frequency factor. So again, what I did is I plotted it with a graph. Now, remember again, I'll try this again, that from our slope-intercept form, this is our y, and this is our x, right? So we plot a graph wherein the y, we plot an ln k versus 1 over t axis here. So again, you use your spreadsheets, you plot this using your spreadsheets, and I've produced this kind of data here. I produced this equation of the line. So again, it's a perfect line, which is again very peculiar, because you don't get a line as straight as this unless it is manipulated. Well, I believe this is manipulated because I think they manipulated it for the sake of just giving an example. But in actuality, you don't get from your kinetic data, you don't get a line as linear as this one. Anywho, so wait, I'll erase this one first. So what will be the how do we get our activation energy and our ln-A? Now, from the slope, the value of the slope is actually this value, as I've indicated earlier, and the value for the y-intercept, which is your ln of A, will be this one. So from these values, you can get these and these. So how did we get that? Now, so since we know that this value is equal to your negative EA over R, the negative sign cancels out, and you transfer this one on the other side of the equation. So what you'll get will be sorry, this one here, right? It's 11201R is equals to EA. But since we all know that the value of the gas constant is 8.314 joule per mole Kelvin, we substitute this value to, this value to here, and what you'll get will be an answer of 93.125 joule or 93.12 kilojoule. So, that's it. Now, for the LNA, for the frequency factor, it's just this one. So it's this one, and we apply our logarithmic property here. So this one will cancel out, and that will be your A. So your A will be 5.163 times 10 to the 11. It doesn't have any unit, actually. It's unitless ang frequency factor. So there you have it. So what if you're not given an equation of the line there? What if you're not given an equation, a set of data there? So what if you're just given 2 data points? So you're just given 2 values of rate constants and 2 values of temperature. By the way, you have to remember that in our Arrhenius equation, our temperature should be in Kelvin. So if it's not in Kelvin, you have to convert it first in Kelvin, okay? So here, if we only have 2 data points, you can use this modified Arrhenius equation here. So how was that derived, by the way? So how was that derived? Again, I'll switch to my board. Wait. Window control. Yep, I'll switch to my board there. So let's say we have 2 data points, which has its own rate constant here. Oops, it's not visible pala. Which has its own rate constant here. Dali ko na lang isulat. So it has its own rate constant here and its own at a certain temperature, and we have this one here, another rate constant at a different temperature for the same reaction. So we apply the what do you call this? The linear form of our Arrhenius equation, which is and the same goes here. Negative sign siya ha. So amuli siya. Now, we'll rearrange the equation such that LNA is on one side and the rest is on the other side. So we transfer these 2 here. So that will become, from positive, it will become negative. So your resulting equation will be so I'm gonna the same goes with the other reactor with our K2 and our T2. So since our frequency factor and this one and these ones are constants regardless of the temperature, so that means Ln Maamo ni siya, right? So then we manipulate the equation such that all the L and K's are on one side and all of the temperatures are on the other side. So our resulting equation will be this one makadto di siya, this one will go here. So they will their signs will change. So from positive it will become negative. So L and K1 minus L and K2 is equal to EA over RT2 minus over RT1, right? Now, since these are the same values and they are constants, they can be factored out, which will give you which will give you, oops, stop shaking, which will give you right, if you still remember your algebra. Now, in your logarithmic functions, again, we know that, I have shown this also earlier in our previous videos of kinetics, that the difference between two logarithmic functions of the same base, like this one, is equal to the logarithm function of the quotient between these two values, the quotient of the two values. So log x minus log y is equal to the log of x over y. And we apply the same thing here, so which will result into which is the one that you see here right in your screen. Okay? So again, we'll use the example again graph that we obtained using our graph, and let's try picking two data points here. So two data sets here. So let's try picking this data set here between 1,600 and 1,700, and we apply this linear equation here. We apply this linear equation here to get the what do you call this? The activation energy. So obviously, you transpose this one on the other side of the equation. Same goes here. So from a denominator, this will become a numerator, and from a numerator, this will become a denominator. So the resulting equation will be, I'll just erase this one. The resulting equation will be this one here. Then you just plug in your values, and what you'll get is the activation energy, which is 93.03 kilojoule, which is really close with what we've got here. But well, that will simply explain because the graph, when you graph this one, it is linear, which is almost equal to 1, which is already 1. But if hindi linear ang imo equation, this one, getting your what do you call this? Activation energy using this method is actually really risky, because here you're assuming that the equation, or the line equation, the linear form, is perfectly linear all throughout the reaction. But since there's no such thing as an r squared equal to 1 that is really perfect, So actually, it is really discouraged that in actual setting that you just use this one here. Not unless if you don't have any choice, or rather, not unless if the data has been well established or the reaction has been well studied nga pwede mo na ni magamit ang amuni nga klase sa amuni nga form sang inyo nga form sang linear formula sa linear equation sa inyo nga Arrhenius equation. Okay? So, then from the activation energy, you just use the regular Arrhenius equation to get the frequency factor. Anywho. So, now let's go to the another model of chemical kinetics, which is the transition state model. Now, in the transition state model, the difference between the collision model is in the collision model, they will, when they, what do you call this? When they surpass or they reach the activation energy upon collision, they will just simply form products. Now, in the transition state model, it is assumed here that, when the reactants effectively collide with each other, they will undergo a fleeting state, which is a fleeting state of the reaction here, which is what we call the transition state. If you can see in the moving graphics here, that when it reaches the peak of the reaction, it forms a complex or some sort of a pseudo reactant, which is what we call the transition state. Or pseudostructure, which is what we call the transition state. Now, again, as I've said, they are transient, or rather, they are fleeting. They do not exist for a very, very long time. They exist in the matter of femtoseconds, which is times 10 to the 19th, negative 19th of a second. So there are already studies that. However, this one has been proven time and time again that the transition state actually exists. There are multiple studies that have proven that there is such thing as a transition state. However, they are very, very short-lived, thus need specialized equipment for their structure to be observed or to be determined. Now, let's go to the reaction mechanism. So, what we have discussed so far is that how fast or how slow the reaction will take place. Sorry. What we have discussed so far is on how fast or how slow the reaction will take place, right? Now, in reaction mechanisms, the reaction mechanisms actually describe step by step how the reaction takes place. Now, let's go to the reaction of nitrogen dioxide with carbon monoxide to form nitric oxide and carbon dioxide. Now, it's shown here that this is actually not a single-step reaction. It is actually a two-step reaction, contrary to what we have shown in what we have shown so far in our videos, in our previous videos. Now, here, two nitrogen molecules will collide to form your NO3, your nitrogen trioxide molecule, and your nitric oxide. And this nitrogen monoxide molecule is the one that will actually react with your carbon monoxide to form your CO2, and it will regenerate your nitrogen dioxide, which will again react to your step 1. Oops. Now, what we have discussed is so far is just one step reaction, and that is what we call the elementary reaction. Now, we will introduce another term here, which is what we call the molecularity, wherein it shows how many units or how many molecules of the reactant actually participate in the step in the reaction, which is actually shown in their rate law. Now, for example, for an unimolecular reaction, only one molecule or unit of the reactant actually participates in the rate of the reaction to form your products. For a bimolecular reaction, although the same reactants, however, there are already two units of them that participate in the reactant formation. Thus, it is bimolecular. And we also have the term molecular. We don't have 4, wherein there are 4 units of the reactants reacting together to form your product, since I think it has not yet been observed. Such thing has not yet existed, or if it does, it has not yet been observed. So it has not been observed, that it was assumed that it doesn't exist yet. There is yet to be proven such reaction wherein there are 4 units of reactant molecules reacts at the same step to form your products. Now, in the one that we have shown, the previous reaction that we have shown, obviously it was not an elementary reaction because it occurs at more than one step. So that is what we call the multi-step reaction. Now, for a multi-step reaction, it should fulfill the following in order for that mechanism to be valid. So one is that for each step of the reaction mechanism, their balanced chemical equation, when you add up those the balanced chemical equation of each step, the result will be the balanced overall chemical reaction. We will see that later on. And also, most importantly, it should agree with experimental data. So let's show first number 1. So let's go back to our reaction here. And as we have shown earlier, these are the 2 steps here. Now, we add this up. So since this one appears on the reactant side, and since this one appears on the product side, they will cancel out each other. Same goes here. One of them will cancel out each other, and the resulting equation will be this one here. So that means our mechanism is correct. And we have seen that the product of one of the products in the first step is also the reactant, one of the reactants on the second step. If you see it here, this one here is the nitrogen trioxide gas. And those reactants are what we call the reaction intermediate. We will show later on where is the reaction intermediate placed in our energy diagram. We have shown it here. Now, the reaction intermediate, as I've said earlier, are the products of the preceding step, which is also consumed in the next step of the reaction mechanism. So we have shown it here. I'll explain that later on. And also, it should agree with the rate law from the kinetic data. So the rate law for this reaction is this one. Now, if you notice here, if you're from going back to rate law, this rate law is only for the first step. It did not consider the second step. So since there are 2 reactions, so what sino nga rate law ang gamiton ta? Should it be this one here or a combination of the 2? Now the answer will lie to this one. Now for the multi-step reaction, the slowest step will be determine the overall rate of the reaction. Thus, the rate law of the slowest step will be the rate law of that reaction here. So that means this will be this is the slowest step in the reaction or your rate determining step. So why do we choose the slowest step? So let's have this analogy here. Now, if you have if you have a highway and there is like some sort of traffic jam, this one here, if you remember this one will cause a traffic jam, right? So the traffic will move more slowly once they pass this part of the highway here. So kung ano kadasig nga mag-move ang ini nga highway, that means dasig man di mag-move ang kuari di sa puno. So that is the analogy of the rate of choosing choosing the slowest step as our rate determining step in our multi-step reaction. And also, since it is the slowest step, it will also have the highest activation energy as shown in our Arrhenius equation. Okay. So as if you remember your Arrhenius equation, the greater the greater the activation energy, the lower will be its rate constant. Thus, the slower it will proceed. Now, how about catalyst? How does catalyst improve, hasten the reaction? We know that when you add a catalyst, it is not exactly consumed in the reaction. However, it hastens the reaction. It hastens the reaction by lowering the activation energy of the rate determining step. Now, it has two cases here. One will be when for an elementary reaction, it just lowers the activation energy of the elementary reaction. Another case here is it lowers the activation energy but changing entirely the mechanism of the reaction. If you see it here, in an uncatalyzed reaction for the decomposition of oxygen, it will it will proceed as a single step. However, when you add a catalyst, let's say chlorofluorocarbon, because usually chlorofluorocarbons is the one that catalyzes the decomposition of oxygen by catalyzing this step. Anywho, that's another different matter. So if you add a catalyst here, instead of lowering the activation energy, this one, it actually splits the reaction into two steps, which is dictated by the presence of two activation energies and also two transition states. Now, since for a multi-step reaction, we only consider the slowest step for the rate law. Thus, since nagdubo na ning activation energy dire, isama lang din i-consider mo, diba? Thus, what will happen is, kung sino ding mas taas sa ila, that will be your rate determining step. But nonetheless, the highest activation energy between these two is still far lower than that of an uncatalyzed reaction. It will certainly hasten the rate of your reaction. Okay, so that's the end of my presentation for this topic. This is again, do not rely on my videos alone. And also do not rely solely on the modules. I've sent you the textbooks. I've sent you a PDF copy of the textbooks. Use that as your supplementary. Use that along with your modules and the videos that I've sent you. So, and again, don't forget to practice in problem solving. So that's it. See you.